Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So, before anything, just as a reminder, remember assignment 4 is in fact out. Take a look at that, and as I promised, the date of that deadline does not necessarily match the one in the course outlines. I'm giving you a couple more extra days to get that finished. So, hopefully that's understandable. I apologize for the delay. So, other than that, are there any questions before we get started? Are we all good to go? Just give me 2 thumbs up if we're good to go. We're going on our fun adventure with Turing machines today. So, anyways, before I proceed, I thought I would talk a little bit about how we could describe Turing machines in a different way. Now, I've been showing you the formal definition of a Turing machine, well, at least one equivalent formal definition of a Turing machine. Also, I've described some machines to you. We've seen some techniques. For example, we talked about how we can match symbols to see if there's equal amounts, for example. I often described this as zigzagging, where I went back and forth, and I would mark symbols, right? This is a common design technique when you're designing your Turing machines. So the great thing about that, I want you to just think about why that's a rather interesting technique, is that if somebody ever asked you, how do I know if there's an equal number of this versus that, say if I have 2 buckets of things, what I can always do is take one and then compare it against the other. And if I see that there's one for each, I account for these, right? This is a common way you can count to see if they're of equal quantities without knowing how many there actually are. And that's exactly what the zigzag technique I showed you the other day does. So, we've already seen kind of like where we can exactly define the Turing machine. But as we deal with much more broader types of languages, some that you would characterize more, instead of talking about a language, you talk about a problem. Remember, I told you about this distinction before, is that the formal notion of a problem is a language. But sometimes it begins to become very useful to start talking about a language as a problem. Because the language itself is just a formality, but really you want to solve some problem. So I thought I would show you an example of this, where what we're going to do is I'm going to, instead of describing in exact terms the Turing machine to you, I'm going to describe it in a higher level based on the design techniques we've seen up to this point. So just as an example, I thought I would consider what is called the element distinctness problem. So this is a problem you may have encountered previously in your studies. So what is the element distinctness problem? Imagine you're given some list of numbers. It could be an array, a list of elements. We'll be more broad, we'll say elements. We can always encode those with bits of information. And of course, I want to know if all of the elements are distinct. So if I give you a list of elements, I want to know if there's a single one of them is equal to another. So if it is in fact the case that the answer is yes, they're all distinct, then I can tell you that every element in that list or array, whatever way you want to formalize it, is in fact distinct. So can somebody tell me what kind of problem is this? We talked about these near the beginning of the class. What kind of problem is this? So notice the way I framed it. Yeah, it's a decision problem. Exactly. So very often Turing machine notions of like the way we use our Turing machine where we have accept and reject, we often were interested when we accept and reject, but we want to make sure the machine always halts. Later on in this class, I'm going to show you the notion of a specific kind of Turing machine that always halts and it'll spit out accept or reject. These are what we call deciders. But I'll talk about that later. The big point I want to get at is when we try to solve a problem like this in the way that we've seen up to this point in, say, your studies in computer science, you may have said, okay, well, if I wanted to solve this problem, like say if we're talking about like a data structures class or just some algorithms class, what you would do is you say, okay, my algorithm has to finish in finite time, correct? And it has to tell me, yes, they're all distinct, or no, there exists a duplicate, true or false, right? So Can somebody tell me, before we get a little too ahead of ourselves, in a language that isn't really like talking about a Turing machine, like in words that you would normally not describe in terms of a Turing machine, can somebody tell me one way to solve this in quadratic time? Don't give me the fastest way, just give me the first thing that comes to mind how you would solve this in a conventional programming language. It has to run in quadratic time. Yeah, so what you would do, so one idea I was going to suggest to you, now of course, an optimal way of doing this would be just to sort the list and then see if there's any that match that are adjacent to one another. But I don't necessarily even need to go that far. Like, technically that's the fastest you can do and solve this problem, given the conventions that we typically use. But there's a much simpler way of approaching this. You can have a nested loop, right? You can have a nested loop where what you do is you check the first element, say x1 against x2, and then you would have, say, the first element get compared against the third one, then the fourth one, then the fifth one, all the way up to the nth one. And then I go to the second element and I compare it against all of the other elements that have not yet been compared. And I can implement this using a nested loop in a typical programming language. And this algorithm would run in quadratic time in that sense. So I'm sure at some point you may or may not have seen this before, this idea that all I have to do is just simply check and compare all the elements, right? So that's one way you can go about that. We can do something like that with a Turing machine. And that's what I'm going to describe to you in a higher level language for you. Like when I say higher level language, I mean description. I should be a little bit clear about the way I'm phrasing this for you. But if you're wondering how you would say, okay, here's the input, here's the answer. I have it in the notes, but effectively the input would be given to you in the following form, where I'm going to have pound signs or hashes, however you want to call them. I'll call them pound signs to be a little easier. Pound or number sign. So I have a number sign, then I have some element of my list. Then I have a pound sign, then another element in my list. Then a pound sign, then an element in my list. I have these separators or marks that are going to separate the elements. This is one way I can encode this information. If I really don't like this first one being here, I can always pad on the sides a pound sign or number sign if I needed to. But this should be okay for describing this problem. So what I'm going to do is I'm going to have n elements. They're going to be separated by these number signs. Each one of them is going to be some binary sequence of zeros and ones. And to be in this language, meaning that when I consider an instance of this, it most certainly has to be the case that it has to answer true for it to sit in this language. Because notice that it has to be that xi and xj, any two elements there where I is not equal to j, they have to not be equal to each other. And I'm assuming that n is greater or equal to 0. So it's possible that there are no elements in my list. So does everybody get the general setup? So I'm going to have this. So for each one of my elements, I'm going to have a number sign, then the element encoded in binary. Then I'm going to have another number sign, then the next element encoded in binary, and so on. So do you see how this language here really represents all of those yes answers to this question, right? So this is like what I was saying at the beginning of the course, is that this is a decision problem, and this language characterizes all of the yes answers, right? So it means that if I give you some string w, and if I tell you it's in this language, then you can say, hey, look, it has that form, and it is indeed the case that all the elements are distinct in how they're encoded into this string. Likewise, if it's not in this language, then most certainly either it looks like absolutely does not look like this in terms of the format of it, it looks like junk, or it could be the case that it has the same format as this, but there exist elements that are in fact duplicates. So does everybody understand the general setup I have here? So I'm going to describe to you a Turing machine that is going to tell me when strings are in this language or not in this language, and it will always halt. So like I said, I'm going to give this a fancy name later. It's called a decider. And when I give you a problem like this, what we do is we say that my Turing machine will decide that language. So it will tell me if it's in the language or not in the language. Like I said, I'll define this later on in the lecture. So I want to give you the idea of how I would approach this. Now, so this is one way you can go about this, but I just really want to give you a flavor for this first before I give you any ideas. So I want to start off with something much simpler, just like I did last time. So, you know, assuming that this thing is a string that is definitely going to be in this language, it's most certainly going to have a form that's going to look something like this. So it may have some blanks afterwards, and there might be a blank. Well, there's a blank that's going to be right here. And there's going to be a sequence of symbols in here. They're going to represent the cells for x1. Then there's going to be a bunch of cells in here for x2. But suppose I only had 2 elements, for example, here. If I only had 2 elements, it would have a format like this if it sits in this language. So if I'm looking at this, I would like to know if any of the elements are the same. Does anybody have any ideas of how I can approach this? How would I determine, assuming I get something on the tape that looks like this? Does anybody have any ideas of how I could determine if this is in the language or not? So suppose, remember, the Turing machine will start right here. Any ideas? Just don't be shy. I'll start probing you with interesting ideas we could try. But I want to give you a moment to think about it. I'll give you a hint. We did something like this last day. Yes, that's exactly it. So remember, there's a whole bunch of cells that are here. There's going to be a bunch of cells that are right here. And then there's going to be these number signs that are just going to tell me when I get to the next element. So if I have some way to determine if these are equal, obviously if they're equal to one another, I better reject, right? If I end up having it where I'm pairing them up, just like I did last day where I had my idea where I zigzag back and forth, if I find out I don't end up having it where they match, then most certainly I'm okay, right? So just the only complication here are these pound signs or dollar signs, not dollar signs, number signs. I knew I was going to say that. The number signs is just really that I need to make sure I have some way of determining when I'm at the next element in the list. But so we have the main idea. We have to kind of zigzag back and forth between these two and check if they're equal or not, right? So just like what we did kind of last day, right? The only difference there was I just had zeros and ones. Here I would just check if they literally are the same. So in contrast, notice here I only assume that I have 2 elements, right? There may be more. So here's an idea of how we can approach this. Here's an idea. So we got the building blocks for this. Here's an idea. I'm going to mark the markers, which are my number signs. So I'm going to designate them a special symbol when I'm going to compare 2 elements. So I'm going to use this to compare 2 elements. So I'm always going to make sure I'm only marking 2 of these elements at a time. So when I say that, I'm looking at the leading number sign. So what'll happen is I'll start off by marking, for example, this one. I may put another symbol on top of here. Some other symbol that's it's among the tape symbols. Some mark that's going to happen here. And I'll try to see if there's another element. If there's another element, I'll mark that one. And then I perform, once I know where these 2 markers are, then I have to do I check if they're equal or not, right? By the same principle I gave you earlier, suppose this wasn't like this, and say there's more elements, then I say I have some more cells. This represents, say, x3, and maybe the blanks here after that. Does anybody see what I can do now once I have this built on top? Is I can move the markers, right? So notice that so now I can try to turn this back to just a number sign, and I can mark this one and compare the first element with the third one, right? And then I could do my zigzag process to check if they're equal or not, right? And then when I'm done that, I move the leftmost one to the next dollar sign. Not dollar sign, sorry, I knew I was gonna do this. Number sign. I should just call it pound or hash, okay? So now notice that I now have some mechanism to know what elements I should be comparing, right? But notice this process is exactly like what I just described earlier with the nested loop, right? So the whole idea is that I'm taking that idea I had where I compare two sequences of symbols, like from last day, and then I embed on top of that effectively a nested loop. So the loop is what does the check between the two elements. And then I'm going to think of this marking process just like if I had another loop that's just going to make sure I go through and I check the markers that are appropriate. So I always make sure that there's always two of these pound signs that are always going to be marked at one time. Does everybody get the general gist of the idea? It's okay if you want to think about it for a little while, but does everybody understand the key ideas? That we have the comparisons that need to happen. I need to know if they're equal or not. If they're equal, then you know for certain you need to reject. However, I'm going to use I'm going to take advantage of the fact that these number signs or pound signs are located here. And I'm going to mark them to help me figure out which elements I'm comparing. As long as I make sure I can do this so that I check all of them, we're okay. So does everybody get the general idea? So notice that I'm not actually describing a Turing machine to you. I'm just describing a high-level description of a Turing machine to you, right? But the same ideas sort of translate from what we talked about last day. So all I do is just do that back and forth process. Remember I was marking X's and Y's, for example, last day? It's the same idea, except now instead of it just being, oh yeah, no, there's a bunch of zeros, I want to match them up with ones. Instead, now you want to check if the symbol in each one of these matches or doesn't match. But yeah, so this is the setup for the Turing machine that I'm going to describe now. So is everybody on board with what I have in mind with this? So just in the back of your mind, think back to how you would test if there's two elements in that list, if they were equal or not, like a nested loop. If you think about it like that, this should hopefully help you give the intuition for this. So does everybody get the general gist of the idea? Just give me a thumbs up if you think we're doing pretty good here. Just don't be shy to ask me. So my idea here I'm going to do is I'm going to describe to you how I'm going to move around these markers and when I'm going to do the zigzag process. So as soon as I do that, you should have enough information to actually describe and pin down the Turing machine. That's going to be the main objective here, is that if I could communicate to you what the Turing machine should look like, then you should be able to see, hey, look, well, I know how to do that. And then, oh, this other thing, I know how to do that too. I could probably describe the Turing machine. It might take a while, though. That's the whole point of why I want to talk about these higher level descriptions, is so that you could still communicate the Turing machine without exactly specifying to somebody, as long as they understand what you're talking about. That's one of those key facets of when you discuss algorithms with people, is that you make sure your audience understands what you're saying. Because we don't want algorithms that are ambiguous. So if we're all okay with that, I'm going to proceed to start describing this for you. So let's move on over here. So I'm going to start off with the first few steps, and then I'll introduce the last two steps. Because I think once you see the first few steps, it's like, okay, well, that makes sense from the picture we just seen over here. So what I'm going to do is I'm going to take advantage of this fact I can mark the number signs or pound signs. So I'm going to take advantage of this fact. So what I'm going to first do is I'm going to attempt to mark the leftmost tape symbol of W. So remember, W is the input. Now, if the symbol is blank, based on how we've encoded the elements onto the tape, then you know there's no elements, right? That means that n is equal to 0, where there's no elements in the list. But that means that there are no elements to compare, right? So that means that you should accept. However, if the first symbol that you run into is not one of those number signs or pound signs, you better reject, because that does not make any sense, right? Remember, you could imagine W being given to you and it's absolutely just like something else saying like kitty cat or something at you. You want to make sure that it does not, actually, well, it would be kitty cat in binary probably. But my point is that if it doesn't fit the form of the language, and we're expecting this to have the number signs or zeros and ones, which those are our input symbols, by the way. If it's on the correct format, then most certainly we shouldn't accept it, right? So we reject if the first symbol we read is not the number sign. That means that whatever we have left, now we can guarantee that that tape symbol, when we first read it, is most certainly going to be that number sign. So now here's what we're going to do. This is how we're going to initially set up this marking process. We're going to scan right to the next number sign or pound sign, and we're going to mark that one. So now we have two number signs that are marked. So we have two of those, just like in my picture I had over here where I first started. I had a mark here and a mark right there. So if you find a blank before you find the number sign, then most certainly that means that X1 only exists, right? Because if we're assuming this form for the strings, then most certainly if you don't run into that number sign, then you're not going to find what you're looking for, right? So that means only X1 is what you're comparing everything against. So you should just accept that means there's only one element. That implies that there's going to be at least two elements otherwise. So now, if it is the case that you do run into that, you have that second mark, that means you have two elements, right? So now this is where I'm going to impose that zigzag process. So I'm going to, by zigzagging, check if the two strings to the right of the marked number signs are equal. If so, reject, right? If they're equal, then you should reject that, because some xi equals some xj. In this case, we're only looking at x1 and x2. But so far, are we doing okay, everybody? So all I've done now is I've set up the process quite similar to the way we did it last class. Except now the difference here is now I have these markers that I'm going to be the Turing machine will move them around and then we'll keep to the right of the markers whenever we're doing a comparison. Do you see how this helps us generally understand the idea? But you could see how conceivably it's a Turing machine that you could actually implement that has this property without having to go through all those states. Because you could actually drill down and actually come up with the Turing machine for this, but it's going to look really, really big. It's going to look really complicated looking at first. It's very time consuming to describe. So I need to tell you what you're supposed to do next, right? I told you that you should be able to move to the next marker to the right, but I also need some way to move that leftmost marker over by one if I need to. So let me describe that step now. So move the rightmost of the two marks to the next number sign, to the next number sign symbol to the right. To the right. Now, just like before, if we encounter a blank before we encounter this, then we know most certainly there's no more elements to look at, right? There's no more elements to look at. So let's try to look at this carefully here. If a blank is encountered before another number sign, move the leftmost mark to the next number sign to its right. To its right. To its right. And now this is the part, you have to be really careful with the way I phrase this. I apologize. And rightmost mark after that, if exists. If exists. So generally this whole process, what I'm just trying to describe to you is that you're going to compare each of the elements. You're going to start with the first one, you compare it against the second, third, fourth, all the way up to the nth. And then when you're done that, you're going to move that leftmost mark over to the right, and then you're going to continue this process comparing the second one to the third, second to the fourth, and so on. And then you're going to then move over to the next one, the third element. You're going to then compare against all of them again, and until you reach all the way until now you run out of. So you're going to eventually hit some point where this is going to have to stop, right? If there is no rightmost mark to be found here. So just to be clear, that's what I'm referring to as when I move to the left. I take the leftmost mark and I move it to the right. That's what I'm referring to here. To be found here. All comparisons have been made. Have been made. You're going to accept if that's the case. However, as you can clearly see that there's still more that has to happen. So if I fall into any one of the cases in here that is not going to accept, that means I'm going to have to restart this process all over again. Well, up to some point. So there's going to be a fifth step. It's just simply go to step 3. So remember, all this is doing is moving over my mark to the right. And when I run out of those, then I move the leftmost mark over to the right by 1. But each time I do this, I'm assigning my 2 elements, right? Some xi and xj that I want to compare. And that means I'm going to need to do the zigzag on it to check if they're equal. And do you see how this process, if I just keep repeating from 3 to 5 over and over again, at some point it's going to have to reject or it's going to have to accept. There is no infinite loop here at all. There is no point for which this is going to just keep repeating on forever. Does everybody see that? But does everybody get the general idea of this Turing machine? Oh yeah, I want to make sure I usually put a quotation mark after this. I'm adopting more of a Sipser style high level description of a Turing machine if you're curious of where or what convention I'm selecting here. Is notice I'm using quotation marks to describe the Turing machine, but this is just another convention for which you can describe a Turing machine. This is more of a higher level description than the ones I've been giving you, because notice that to do this takes a lot of work, and I'm hoping that the final problem on the assignment should give you some appreciation for doing this. So, are there any questions about this? Or are we doing good? I just want to make sure that it's clear and that we can design Turing machines that even can solve problems that you'd write with a normal conventional computer, right? So like checking if there's if all the elements in an array, for example, is a pretty conventional problem that people would encounter in programming. So if we're okay with this, I'm going to proceed now. So keep in mind, this full description is in the notes. So if you find yourself just staring at this like, I don't know, man, there's a lot of stuff on that board. Don't worry. Feel free to take a look at the notes if you find yourself wanting to just check something I've written here carefully, okay? So, is it okay if I proceed to talking about the language of a Turing machine? Here, I think we're good. Let's proceed. So I want to proceed. So I'm hoping this gives you a variety of different techniques that you can try for designing a Turing machine. And I've given you a couple of different ways that you can describe them. You can describe them at a machine level, where I am literally just saying, hey, look, here's my Turing machine. Then there's also this higher level description. Now, obviously on like an assignment, I'll be very clear about how you should describe it to me. For example, on the fourth assignment, you should most certainly be describing to me in an exact way, not this higher level way. You can design it on a machine level way, just like this higher level one. But the point here is I'm just trying to show you that once everybody sort of agrees on certain design rules of a given machine, you can actually describe them a little bit more informally like this to somebody if they understand what you're saying. Why? Because these Turing machines can get really complicated really fast when you want to do some really interesting stuff. So I want to talk next about the language of a Turing machine. So I must stress that there's several equivalent ways to define the language of a Turing machine. So that's the first one I need to point out to you, is that there are many equivalent ways to define the language of a Turing machine. So the way I'm going to show you here is going to be based on acceptance, just like what we would expect from all of our working examples. But I'm going to show you how you can use instantaneous descriptions. Remember those IDs I showed you with the PDAs? There's another equivalent way of doing this with Turing machines too, but it's not exactly the same. It's quite similar though. So let us use a kind of instantaneous description. Remember, the point of the instantaneous description is to describe the current configuration of the machine. That's really what the instantaneous description's purpose is to show you what the configuration of the machine looks like so that you can describe formally what a move looks like. So when I talked about a PDA, what mattered? It was the state it was in, what's currently left of the input, and the stack, what the stack looked like. So naturally, when you think about a Turing machine, you have to think about that tape, right? And the state I'm looking at. And generally where I'm going left or right, for example, on the tape. So one thing I want to point out, and this is something that usually people will ask, okay, well, how do you describe the state of a Turing machine? Because surely you might say, Dan, the Turing machine has its tape goes infinitely in either direction, right? It goes infinitely to the left, infinitely to the right. So how the heck do you describe that to somebody, right? Well, here's an interesting fact. So this is just something that you should keep in mind. So if we only actually, we'll say if we only make a finite number of moves, then the Turing machine can only scan a finite number of cells, right? So we only really have to care about what happens in this process, right? So this observation allows us to describe the tape like an ID. So you already see that. So if I move to the left or to the right from a given cell after reading it, notice that if I do some finite number of these, most certainly it must be the case that whatever's on the tape that I've modified or read has to be of some finite quantity. Sure, that might mean that if there's a lot of moves, there might be a very lengthy description. But well, all we have to do is we show only parts with our input and where the moves have occurred. Right? That's all I really care about. Because remember, I can have it where I move along all the way along a tape and write a whole bunch of blank symbols, right? So we might have to account for both of these, not just the input. But when you initially describe the ID, it would just simply be the input, but you may have it where if you go slightly to the right of the tape, beyond where the input is, you're going to have to describe this too, right? But usually the convention is really, if the input is the only part that really matters, you just write the input. If you find yourself with a bunch of blanks between parts that you're writing, then you have to write those. Otherwise, it's really unclear what you're doing. Because remember, we want to describe the current configuration of the Turing machine. So, for example, if I give you delta p xi like this, and I say I'm going to make the following move, or I'm going to replace xi with y, and then I'm going to move left, here's how I would describe it to you. Like I said, I'm not going to use this notation really a whole lot. I just mostly want to expose you to it. So suppose that x is the input, so x1, x2, all the way up. And suppose at this point, like this is whatever is currently on the tape at that moment. I'll usually encode the state on the ID itself. So I have xi plus 1, all the way up to xn. And I'm going to use this turn side notation just like I did with the PDAs. So I have x1, x2, all the way up to xi minus 2. So, okay, so remember, prior to the move, I'm in state P. So that's why P is located right here. It always is drawn to the left of the symbol it is being read at. So just keep that in mind. So if you see a P right here before the symbol that's on the tape, that just means that it's currently in that state, and it is in fact the read that head is in fact pointing right here. Then, so I move to the left after I write the Y. So that means that now I'm going to be in state Q. I've moved to the left. So it means I'm at this symbol on the tape. That's where the head of this machine is currently at. And of course, that means that the XI is now a Y. XI plus 1 all the way up to XN. So notice that there's at least a couple things being encoded here. Everywhere to the left of the current symbol I'm looking at, my head, that's where the state is. And whenever I make moves, I always put it to the left of where the head on the tape is. So does everybody see this? Just want to be clear. So the reason why Q is written beside XI minus 1 over there is because I moved left on this move, and that's why it's there. So just keep that in mind. This is just a convention for drawing out the instantaneous description of a Turing machine. So naturally, I can always tell you that, hey, look, I also use the same notation as I did for the PDA to describe 0 or more moves. So these instantaneous descriptions I have here are most certainly just like how we used it with the PDA. So now I want to use this notation to describe to you the language of the Turing machine, at least in the way that we've been using it. So let's proceed over here. Let's proceed over here. And let me formally define this for you. Okay, so let's define the language of a Turing machine. So language of Turing machine. So here's how I'm going to define it for you. So let T, the Turing machine, M equal to the following 7 tuple. Q, sigma, gamma, delta, Q0, blank, F. The language recognized by M, denoted by L of M, is the following. Is L of M is going to be equal to, so if I give you some input W, consisting of input symbols, here's how I'm going to describe it to you. So remember, when the Turing machine starts up, it's sitting at the leftmost tape symbol that has our input, correct? So it means when I describe this to you, in terms of an instantaneous description, remember, I always write the state of the machine to the left of where the head of the machine is, right? But the whole input is sitting right here, right? So this is the initial configuration of the Turing machine. Does everybody see that? And then a whole bunch of moves may happen. And then there might be some sequence of tape symbols on the tape here. Then there's going to be some QF that I might get into with beta right here, where QF is going to be a final state, and alpha and beta are going to be in fact, consisting of tape symbols. That's what the star means here. It means 0 or more. 0 or more tape symbols. The point here is that it's sitting into it's in a final state. Does everybody see that? So there may be symbols to the left of where the head currently is sitting. It will be sitting at the first symbol that's sitting in beta. But notice the state is QF, which belongs to, it's one of the final states. So this is a formal description of how the Turing machine will in fact accept. So just to be clear, that is, if M enters eventually a final state, then the input is accepted. The input is accepted. Otherwise, now this has got to be the most overloaded otherwise I've ever used in this class up to this point. Otherwise, it is not. Now remember, that does not mean reject always. Just to be clear, remember this thing, there's always the possibility that the machine may never halt, right? So first, are we okay with this definition for the language of the Turing machine? So remember, the instantaneous description's job is just to tell me what the configuration of the machine is. And the first, this Q0W, that is just the initial configuration of the machine. I encourage you to think about it. Then this is just simply saying, hey, look, I'm in QF. That's the current state I'm in. There might be a bunch of tape symbols to my left and to my right. That's all it says. So I want to spend the last 2 minutes just defining a couple of important things for you. So let me define these two important sets that are going to be very important for the rest of our discussion at some point here. So there's two sets of languages of interest for Turing machines. So the first one is what we call the recursively-enumerable languages, which are sometimes called the Turing-Recognizable languages. So the recursively-enumerable languages, which are, it's often written as RE as an abbreviation. And this is sometimes called Turing-Recognizable. Turing-Recognizable. So the first one here is recursively-enumerable. The name of it comes from some work that is precursor of Turing's work. But the name should naturally, for anybody that's familiar with or heard of recursion theory, a lot of the work around that is kind of closely related to why we call it this. But I'm not going to go into those details here. It's more of a historical thing with respect to our class. So this is just simply the set of all languages that can be accepted or recognized by a Turing machine. So when I say that, if I give you some language and I present to you a Turing machine that is able to accept or recognize, remember that doesn't necessarily mean that it's just going to be able to halt all the time. It just means that it's always going to, if the string is in that language, it's going to accept always, but it may do other things. It may reject, it may never halt for strings that are not in that language. We say that that language is what we call recursively enumerable or Turing recognizable. Another one is the so-called recursive languages. So recursive languages. These are what we call Turing-Decidable. The recursive languages we mostly denote it as an R. This is often called Turing-Decidable. And this is what the phrase I was using at the beginning of this lecture was about. So recursive languages or Turing-Decidable. Again, the name recursive, it's a historical aspect of computability theory. That's where its name comes from. It doesn't have to do with like, oh yeah, I'm computing the nth Fibonacci number. That's not really what it's about. It's another name for the possibilities of computing. So I want to consider a Turing machine that halts on all inputs These are called deciders. So you know how I had transducers the other day? These types of Turing machines are called deciders. Likewise, some people would refer to the Turing machines for the for a language that's recursively enumerable or Turing-Recognizable. They'll call these recognizers, just to be clear. So these are so-called deciders. And the way this works is it always has to make a decision to accept or reject. Do you know that middle issue where I had it where, oh yeah, no, there might be a case where if I give you a string that's not in the language, it may never halt. This is going to be something that does not happen for a decider. It must always halt. And it'll tell you accept or reject. If it accepts, it means it's in the language. If it rejects, it's not in the language. Just like the first example I showed you this today. So these are called deciders. So if I ask you for a decider, you know exactly what I mean, because this should sound like something else, a little bit more informal to you. So this is just simply the set of all languages, and I will be wrapping things up here in a minute here. My apologies. The set of all languages. Set of all languages that can be accepted, recognized, using a decider. And any one of these languages I would refer to as a Turing-Decidable language or recursive language. Now, next day when we come back, I'm going to give you a couple of intuitions around both of these sets because they seem a little bit like, okay, well, why do you need one versus the other? I'm going to focus primarily on this latter one because at this stage, you might think of this as something that I've naturally tried to draw upon earlier in this lecture. You remember I talked about the element distinctness problem and I said to you, oh yeah, well, you can think of it like a nested loop, right? And you always want to make sure that when you design an algorithm, it terminates for all inputs. Notice that this is a very common feature when we describe an algorithm to somebody. I'm just saying, it looks very similar to that notion, right? So we'll talk more about that next day, okay, everybody? That being said, I want to say thank you very much and have yourself a beautiful day. I'll see everybody later.